Hello everyone, in this video we are going to talk about constitutional isomer and how to draw it out based on the molecular formula. So when we are looking at the isomer, that is a concept or a group of molecules that share the same molecular formula. Meaning that they have exactly the same thing, same number of carbon, hydrogen, oxygen, whatever they have there, they have exactly the same number of them. And in order to be considered as constitutional isomers, the molecules we are looking at here will have different connectivity. So what does that mean? Let's look at one example. So first we are going to look at C3 hydrogen 8 oxygen. So we are going to just draw some molecule out in the Lewis structure for now. So the first one is to have all this carbon oxygen connect with each other, and this is the first we can draw out. That is a alcohol. Okay, have an OH, and this is a Lewis structure. So basic connectivity is the carbon, oxygen connect together. They are all higher multivalent items, so we connect them together first and then put the hydrogen around them to fill up the tetravalence of carbon and divalent of oxygen. And that is the first one. The second one, what we can have here is carbon, oxygen, carbon connectivity, and we fill in the hydrogens to satisfy the tetravalent and put the lone pairs on the oxygen to give octet to the oxygen. So what we are seeing here is these two are constitutional isomers. They have exactly the same number of carbon, hydrogen, and oxygen, but the connectivity are different. So the first is an alcohol, OH group right here, and second is ether. So if we simplify them, so the first one, a skeletal structure will look like this. At this moment, we'll put lone pair on there, and the second will look like this. So they are different molecules. They are constitutional isomers. So there is a good example students always get confused is, for example, CH2CHCl2. Okay, so this is dichloromethane. So if you draw out the Lewis structure, some student will do this, and probably your neighbor will do something like this. So for these two Lewis structure, what we are seeing here is they exactly represent the same molecule. Why is that? Because this carbon connect to two hydrogens, this carbon connect to two chlorines. That's it. So connectivity are the same, and there are no difference here. So they are the same molecule. So let's just, they are not constitutional isomer. Now you may have a question how we can draw out the constitutional isomer. So before that, what I want to do here is to introduce an idea of degree of unsaturation. We'll write it out right here, degree of unsaturation. So degree of unsaturation basically is a calculation based on the formula that will tell you the structure feature of this molecule you are going to draw that satisfy the molecular formula. So degree of unsaturation, this calculation is like this. So if you are giving a molecular formula, the number of carbon inside times 2 plus 2 and minus the number of hydrogen and plus the number of nitrogen and then minus the number of halogen, exit halogen. So divide by 2. So 1 minus hydrogen and minus halogen. The same thing here. It is because halogen and hydrogen both are monovalent. So in terms of the degree of unsaturation, their contribution would be the same. So degree of unsaturation. So what that degree of unsaturation tell us in terms of the structure feature? So if the degree of unsaturation equals to 0, meaning there is no pi bond or ring inside the structure you are going to draw. You may ask, what is the ring? So this is a linear molecule. This is 5 carbon connect with each other. So that's an acyclic. And the ring basically is a cyclic structure. For example, if we connect 4 carbon like this, so this is the ring. This is cyclic. This is acyclic. Ring is a cyclic structure. So when degree of unsaturation equal to 0, you will not see anything like this inside your molecule. It always needs to be acyclic. Okay. And when you have degree of unsaturation equal to 1, so the scenario here is the molecule you are going to look at it, there is 1 pi bond or 1 ring. Okay, so you will see either a pi bond or a ring inside this molecule that satisfy that degree of unsaturation equal to 1. So in this case, if we have degree of unsaturation equal to 2, so there will be 3 scenarios. The first scenario will be the molecule you are looking at here will be 2 pi bonds, or it have 2 rings, or it can have a combination of 1 pi bond and 1 ring. Okay, so that is degree of unsaturation. So now let's revisit what we have: C3, hydrogen 8, and oxygen. Let's switch another page. Carbon 3, hydrogen 8, oxygen. So based on the degree of unsaturation, this scenario here is 2 times 3 plus 2 minus 8 divided by 2. And that gives us a 0. So what we are going to draw here will not have any pi bond or any rings. So the first one, what we can have here is carbon, carbon, carbon. Oxygen connect with each other. And I call this backbones. So the molecule you are going to draw here is zigzag, carbon, 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 1, 2, 3, oxygen. And oxygen have to have the hydrogen in order to satisfy divalent. And then that's it. That is the first molecule. You should not have any double bond or triple bond, the pi bond on this molecule. So the next one, what we can have is carbon, carbon, oxygen, carbon. That is 4 linear together for now. And this is this is the second backbone. And what we can do here is carbon, carbon, oxygen, and carbon. And we'll put the lone pair in. And you may say, do I need to check? As long as this structure satisfies the degree of unsaturation, and you are sure you have correct number of carbon, and in this case of oxygen, and you fill in the hydrogen on the hinter items, the hydrogen number will be correct. Okay, so that is the first 2. The third scenario is we are going to decrease the backbone size by decrease the number of the items. So we can do carbon, carbon, carbon. That's 3 of them, and then we can have oxygen in the middle carbon. Okay, so that is another way we can create this backbone. So for this case, if we draw it out, carbon, 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 and oxygen right here need to have a hydrogen to satisfy the divalent. And that is the third scenario. So you may ask, what if we have carbon, oxygen, carbon? Let's see what would happen. So carbon will be right here. Immediately what we see is we have 3 bonds around oxygen, so that oxygen cannot be neutral anymore. So this scenario will not be an option. So what we are seeing here is for this carbons 3, hydrogen 8, and oxygen, by doing the degree of unsaturation, draw out a backbone, and we can have 3 constitutional isomers. for this molecular formula. Now we are going to decrease the number of hydrogen. That will increase the degree of unsaturation. So what we are going to look at here is carbon 3, hydrogen 6, oxygen. So this is the typical procedure when you are giving a molecular formula and asked to draw out all the possible constitutional isomers. The first thing is to calculate degree of unsaturation, to write out what kind of features the constitutional isomer molecules would have. So for this one, 3 times 2 plus 2 minus 6 divided by 2. And that is 1. Degree of unsaturation equal to 1. So we will have two scenarios. You can have one pi bond in your structure, or you can have one ring. So two scenarios. Let's separate them. Okay, so two scenarios. So on the left side, one pi bond. The first we can do is, again, carbon, 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 oxygen backbone. So for this backbone, let's draw it out. 1, 2, 3, oxygen. Now what we are going to do is, this is the backbone. What we want to have here is to have a pi bond. So the first pi bond we can have is between these two carbons. Then immediately we need to fill in this hydrogen in order to satisfy the divalent of oxygen. And then the second one, we are going to use exactly the same backbone. Carbon, 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 oxygen. Now we can move the pi bond. And the second place we can have this pi bond is between these two carbons. So in this case, what we need to do here is fill in that hydrogen to satisfy divalent. And we'll come back to this carbon-carbon oxygen backbone. Right here, we can also have the pi bond between carbon and oxygen. So what we are doing here is using the same backbone, and by moving the pi bond position, we can create 3 constitutional isomers in this case. So the next backbone, what we can have, still we can have 4 items together. So we will have carbon, carbon, oxygen, carbon as a backbone. So we will draw out the backbone number 1 like that, and we can have pi bond between these two carbons. Fill in the lone pairs at this moment. Okay. So now you may say, let's try to move this pi bond again. Let's try to move it. So we move it here. Immediately what we see is 3 bonds around carbon. Oxygen, that is not going to give oxygen a neutral. So that is not the option. So that is the only option for the carbon-carbon, oxygen-carbon bond where this pi bond can be. Okay. So that is when you have 4 items along the line. So now we will reduce that number by 1. So we'll have 3. So 3 carbon, 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 oxygen to begin with. So basically backbone will look like this. Now we are going to put the pi bond in. First option, pi bond between carbon and oxygen. Then you will have this carbon-oxygen double bond. Okay. We can also move that pi bond between carbon and carbon right here. So that will give you the second one with this backbone. And remember to have that hydrogen next to the oxygen. Okay, so that is the third option. And the fourth, let's see if we can have a backbone something like this. Immediately what we see here is 3 bonds around oxygen, so that is not an option. So that is all the constitutional isomers that have a pi bond. All these 3, 4, 5, 6. Now let's look at the ring options. So we have 3 carbon and 1 oxygen. So in order to form the ring, right, the atom at least need to have 2 bonds, meaning that it has to have at least a divalent or trivalent or tetravalent atom to connect. We have carbon and oxygen. So we have 4 of them together. The biggest ring we can have is looking at like a square. So we have carbon, 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 oxygen connectivity. So to put that in a skeletal, it will be something look like this. Okay, So that is the first option. The second option is we can have carbon connect as a 3-member ring, and for this one, oxygen will be on one of this carbon. So you may ask, can I draw this oxygen on the top of the carbon? This carbon? Any of them will be okay, because what we are seeing here is just a carbon as a triangle ring, and then you will have oxygen connect to one of them. So for this one, what we will have here is this molecule. And for this 3-member ring, what we can also do is swap one of the carbon that will have carbon-carbon oxygen. And in this case, we'll have to have the carbon with one other carbon, because if we connect this carbon to the oxygen, oxygen will not have only 2 bonds around it. So that is the third scenario. If we draw it in bond line, so what we are having here is this molecule right here. Let's put lone pairs for now. Okay. So for the ring option, what we have here is 3 of them. So that is the constitutional isomer for carbon 3, hydrogen 6, and oxygen. So this is a little more complicated situation right here. So systematically draw out the constitutional isomer. So the next, let's look at a little more complicated cases that we will start with a molecule that is given. So this one. Immediately, if we examine this molecule, it has a ring, it has pi bond. Degree of unsaturation equals to 2. Okay, and if you don't believe me, let's do this. Let's write out what a molecular formula. So on this molecule, you have 3 carbons. You have, let's see how many hydrogens. You have 1, 2, 3, 4, and 5. So you have 5 hydrogens, and you have nitrogen. So if you take the degree of unsaturation, it is 3 times 2 plus 2 minus 5 and plus 1 divided by 2. So we get here is equal to 2. Okay, degree of unsaturation equal to 2. Let's see. We will have 3 scenarios. The first one is 2 pi bonds. Or we can have 2 rings. Or we can have 1 pi bond and 1 ring. Okay, 2 pi bond situation. So 2 pi bond need to be linear because it's acyclic. It doesn't have the ring. So what we can have here is we have 3 carbon, 1 nitrogen. The first scenario is we can have carbon, nitrogen. Start from the longest chain possible. So these 4 items will connect to each other. So what we are having here is, first of all, we can have carbon, nitrogen. So we can have 2 pi bonds. Those 2 pi bonds can be together, meaning that you form a triple bond, or you can separate them together. So if we have 1 pi bond here, the other pi bond has to be here. So this is a common mistake students will make. So they say 2 pi bond, okay, let's do this. 1 is here. 1 is here. So this is incorrect. Okay, this is incorrect. So never put 2 carbon double bond together next to each other. Okay. So that is not an option. So we cannot put those 2 pi bonds together. So because we only have 4 items, so the only option to have 2 pi bonds separately is this scenario for this backbone. However, we do have the ability to put 2 pi bonds together to form a triple bond, because triple bond is 1 sigma bond, 2 pi bonds. So 2 pi bond together, triple bond, we can put in between the first 2 carbons. So those 2 carbons have triple bond, and then this connect to the third carbon, and then carbon connect to nitrogen. So I'm going to label these carbons for your reference. 3, 4, 3. So this is 1, this is 2, and this is 3. Now we can also have those triple bonds start to move to between the carbon 2 and carbon 3. So in that scenario, I'm going to actually draw the triple bond first. That is my carbon 2 and 3. 2 and 3, since it is sp carbon, so we draw it linearly. So carbon 1 is right here, and then have NH2. This is second scenario. Now we are going to move those two triple pi bond towards the nitrogen. So we can do that because the nitrogen can have 3 bonds when it's neutral. So nitrogen is right here, and this is carbon 3, and for carbon 3 connect to carbon 2, and this is 2 and 1. So this is your 2 and this is your 1. So that is the first backbone, carbon, 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 nitrogen, that we can have 4 constitutional isomers to have 2 pi bonds. And the second scenario, let's draw it out. Carbon, carbon, nitrogen, carbon. Let's see how many we can have here. The first option, again, we can have 2 separate pi bond, or 2 separate double bonds. So one is here, one is here. Okay, that is only separate double bond for this one. And then let's see if we can have triple bond. So we'll call this 1 and 2 and 3. Okay, so let's insert a triple bond between carbon 1 and carbon 2. So this 2 pi bond will be here, carbon 1, 2. And then the nitrogen next door. And then we'll have this carbon 3. So for this nitrogen, it has to have a hydrogen on it. And then the next you may say, let's see if we can move this 2 pi bond between carbon 2 and the nitrogen. So if we are looking at the backbone right here, at this moment, this nitrogen already have 2 bonds. So if you add 2 more, this nitrogen will have more than 3 bonds. So it will now be neutral. So in this scenario, you will not be able to move those 2 pi bond or move this triple bond further. So that is the only 2 constitutional isomer with the carbon-carbon, nitrogen-carbon backbone. So now let's move on to see if we can reduce the number of the backbone and have 2 double bond, 2 pi bond, excuse me. So carbon, 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 nitrogen first, and then we can have carbon, nitrogen, carbon, carbon. Okay, right here. So for both scenarios, let's examine it. So at this moment, we still need 2 pi bond to put in, or 2 bond to put in. So this carbon already has 3 bonds, so the maximum it can have is 4. So there is no way we can put another 2 pi bond in this structure. So this one will not work. And same reasoning for this one. What we are seeing here is nitrogen already have 3 bonds, so you still need to insert 2 bonds, and there is no way we can put 2 bonds there in order for the nitrogen to be neutral. So this cannot be another backbone. So that is the whole thing. For the 2 pi bond scenario, we can only have 1, 2, 3, 4, 5, 6 constitutional isomers. So the next will be 2 rings. So 2 rings, so we will have 2 acyclic structure together. So the first scenario we'll have here, we only have 4 items. So the first scenario will be you have carbon, 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 and carbon, the other side is nitrogen. And second scenario is we swap one of the carbon with nitrogen. So something like this. So if we draw it out, the first one look like something look like this, pretty crazy looking, and the second one will look like this. So this is the 2 that will have 2 rings. So hypothetically, you can draw it out. This is satisfying the degree of unsaturation, the molecular formula. In reality, these 2 molecules will now be existing very low energy level because it's highly unstable. It's very hard to make probably. So we will just leave it as it is, but those are 2 scenarios that have 2 rings. So the last one will explore the 1 pi bond 1 ring. So the first one we have here is our given molecule that already have 1 ring and 1 pi bond. So this ring is 4-member ring because we have 3 carbon with 1 nitrogen. So the next what we are going to do is we are going to keep this backbone, carbon, 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 nitrogen ring, and we are going to move the pi bond. So the pi bond will be moving right here. Okay, right here. So you may ask, can we move the pi bond here? So these 2 molecules actually are exactly the same thing, because if you imagine yourself flip this molecule 180 degrees, that is just like this. So these 2 are the same thing. So in this scenario, what we will have here is 2 constitutional isomers with 4-membered ring here. Now we are going to decrease the size of ring. The smallest one will be triangle. So the first one we have is carbon, carbon, carbon. Then you will have 1 nitrogen connect to one of this carbon. And then for this backbone, we are going to put the pi bond in. So first one, let's put the pi bond right here. Okay, and then this nitrogen need to be NH2. Okay, and then we will go back to the backbone. And now I'm going to move the pi bond here and NH2. And then third scenario is I'm going to move the pi bond outside of the ring and between the 20 carbon with nitrogen. That is the third scenario. You may ask, can I move this pi bond to this, in between these 2 carbons? That will give you exactly the same molecule as this one. So that is a repeat. Okay, so this is 3. And for the 3-member ring, we can also have our carbon, carbon, nitrogen ring. And for this scenario, we can have carbon right here, or we can have carbon, carbon, nitrogen, and one of the carbon connect to another carbon. So these 2 are the other 2 3-member rings. So we are going to finish this up here. So the first one, we have nitrogen right here. And for this one, the only place we can put pi bond is right between these 2 carbons. Why is that? Because at this moment, the nitrogen already has 3 bonds. We can now move that pi bond anywhere else. So for the last 3-member ring, what we have is this backbone right here. So the first pi bond we can form is between these 2 carbons. And then the second we can form pi bond is between these 2 items. And these 2 are different. Why? Because this carbon don't connect to a carbon, but this carbon connect to a carbon. So these 2 carbons are different carbons. And then the last one, run out of space. Let's see if I can move it a little bit. Now the next one is we can also move the pi bond inside ring to this position right here. So in this scenario, your nitrogen need to have a hydrogen on it. And then there will be the last one that we are going to move this pi bond outside of the ring between those 2 carbons. So it's right here. And hydrogen, nitrogen again need to have hydrogens. Okay, I'm going to put the lone pairs on the nitrogens. Okay, so that is another few constitutional isomers that have 1 ring and 1 pi bond. So that is the end of the video. So I hope you learned how to use degree of unsaturation to draw out all the possible constitutional isomers. Thank you for watching.